Welcome to lecture 4.6, some special orthogonal functions. This is that fun lecture that I've been hyping up over the last few lectures, and we're going to revisit some ODEs from physics and engineering that I briefly showed you when we studied how to solve ODEs using power series and generalized power series. And what we'll do now is I'll show you how these are all secretly Sturm-Liouville equations. So we're not going to actually solve these. That would take the fun out of the lecture. I'll just tell you what these solutions are, and I'll show you how they are orthogonal with respect to the special weighted inner product, and then I'll show you what a generalized Fourier series looks like. Okay, let's get started. This section of lectures is all about Sturm-Liouville equations. I want to now return to something that I mentioned in passing that I promised to revisit with examples, and that's that every second-order linear homogeneous ODE can be written in self-adjoint or Sturm-Liouville form. Now, what did I mean by that? So here's a second-order linear homogeneous ODE, y double prime plus p of x y prime plus q of x y equals 0. So we typically write it in this standard form where the y double prime is monic, but what we could do instead is we could write it to look like a Sturm-Liouville equation, or at least the left-hand side. So we could find functions little p and little q and write this as negative ddx of little p of x y prime plus q of x y equals 0. So up here, this is Ly equals 0. So solutions to this second-order ODE are things in the kernel or the null space of the Sturm-Liouville operator L. Now your standard Sturm-Liouville equation is an eigenvalue equation, so it's Ly equals lambda w of x y. So there's clearly no w of x in this equation. So really what I meant by this is that the homogeneous part can always be written as a Sturm-Liouville operator applied to y. And here little p, little q, w are obviously positive functions. Now, many of these ODEs that come up in practice in physics and engineering require the Frobenius method to solve. And I actually showed you some of these when we learned about that method. And now we're going to revisit them. The first one is Legendre's equation. This is 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 y equals 0. So this is used for modeling spherically symmetric potentials in the theory of Newtonian gravitation and electricity and magnetism, things like the wave equation for an electron in a hydrogen atom. Now, I have not written this in a Sturm-Liouville form, and there's actually no lambda. So when you see things like this, n times n plus 1, it turns out that that is actually going to be the lambda. So this is usually how we see these ODEs. What I will do in this lecture is I will show you how we can write this, or what it looks like when it's written in Sturm-Liouville form. The next one is parametric Bessel's equation. Now you've seen the regular Bessel's equation, which is a special case when lambda is 1, but the more general form is x squared y double prime plus xy prime plus quantity lambda x squared minus nu squared y equals 0. And this is used for analyzing vibrations of a circular drum. Chebyshev's equation, 1 minus x squared y double prime minus xy prime plus n squared y equals 0. This arises in numerical analysis techniques. Hermite's equation is y double prime minus 2xy prime plus 2ny equals 0. This is used for modeling simple harmonic oscillators in quantum mechanics. Laguerre's equation is xy double prime plus 1 minus xy prime plus ny equals 0. This arises in a number of equations from quantum mechanics. And finally, Airy's equation, y double prime minus k squared xy equals 0. This arises in models of the refraction of light. In this lecture, we're going to examine in detail these first 4 equations. I'll leave exercises from the last 2 for homework. Here's our first example, Legendre's differential equation. So right away, I'm going to write it in Sturm-Liouville form, defined on the interval negative 1 to 1. So negative ddx of the quantity 1 minus x squared times dy dx equals lambda y. So this is a Sturm-Liouville equation because p of x equals 1 minus x squared, q of x is 0, and w of x equals 1. And right now I'm realizing a slight oversight that I said. I've said that p of x has to be positive, yep, w of x has to be positive, and I should have said that q of x has to be non-negative, because there's going to be a lot of equations when this is actually 0. Okay, so this is a Sturm-Liouville problem defined on the open interval, because on the endpoints, p of x is 0. The eigenvalues of this Sturm-Liouville problem are n times n plus 1 for positive integers, and the eigenfunctions then are solutions to this ODE, and if we plug this in for lambda, we get what's typically known as Legendre's equation, which I showed you in the previous slide, and here it is. Now, let's think back to when we solved ODEs like this using the power series method. Recall that in at least one example, we had one solution that was a power series, had infinitely many terms, and the other solution, eventually the terms became 0 and we got a polynomial. That's what happens here as well. So for each n, one of the solutions is a degree n polynomial called a Legendre polynomial. So we have one of these for each n, and it's defined as Pn of x like this. So it's 1 over 2 to the n factorial times the nth derivative of x squared minus 1 to the n. These polynomials, these are eigenfunctions of this ODE, and they are orthogonal with respect to the inner product defined as f dot g equals the integral from negative 1 to 1 of f of x g of x times the weighting function 1 dx. It can be checked, it's messy but it's easy, that the inner product of any two of these Legendre polynomials, so Pm and Pn, which is just the integral of their product from negative 1 to 1, is 2 over 2n plus 1 times delta mn. In other words, this is 0 if m and n are different, and if m and n are the same, then it's 2 over 2n plus 1. By orthogonality, every function f of x continuous on the open interval from negative 1 to 1 can be expressed using Legendre polynomials. In other words, f of x equals the infinite sum from, I'm going to say 0 to infinity because I'm going to allow the constant function, of c of n times Pn of x. And we have an explicit formula for Cn. As before, it's the inner product of f with Pn, the degree n Legendre polynomial, divided by the inner product of Pn with itself. And again, this is just normalizing it because these things are typically not unit length. And so if we plug in this formula, Pn.Pn, we have a formula for that right here. That's 2 over 2n plus 1. This is the reciprocal of that is just n plus 1/2. So our formula for Cn is n plus 1/2 times the inner product of f with Pn. So it's really just that simple. Okay, so it's really messy if you do the details. And I think maybe I signed for your power series homework things like solving Legendre's equation. So I don't remember which one I would have assigned, but I'm pretty sure that at least one of these equations that we're doing in this lecture, you've already done for homework yourself. Here are the first few Legendre polynomials. So the first one, P0 of x is 1. The next one is x, then 1/2 times 3x squared minus 1, and so on. I don't need to read them out. Here's what they look like, or at least the first 6, from n equals 0 to n equals 5. And I think it's remarkable that we can write an arbitrary function on this interval as an infinite sum of these guys. Isn't that remarkable? Well, I think it is. Okay, here's the next one. Parametric Bessel's differential equation. So this is a more general form of Bessel's equation that we solved in section 2. So consider the following Sturm-Liouville problem on the interval 0 to a. So negative d dx of xy prime minus nu squared over xy equals lambda xy. So this is definitely in the Sturm-Liouville form. And p of x equals x. Q of x is negative nu squared over x. And here the weighting function is x. That's no longer constant. For a fixed nu, so nu is not lambda, it's just another constant here, but we have an equation like this for each nu. The eigenvalues of this equation are omega n squared, which I'm defining to be alpha n squared over a squared. And here, alpha n is the nth positive root of that Bessel function, j nu of x, which is the Bessel function of the first kind of order nu. So I know that's a lot to take in now, but again, we're not going to be solving this explicitly. I'm just summarizing what the solutions are. The eigenfunctions corresponding to these eigenvalues solve the parametric Bessel's equation, which if you multiply this thing out is just the thing that I showed you a couple slides ago. If you fix nu, then for each n, there is a solution which I'm going to denote as j sub nu n of x, which by definition is j nu of omega nx. So think of j nu as the Bessel function of the first kind of order nu, and then by this omega in here, we're dilating it. So it's sort of like what we do with Fourier sine and cosine series when we look at sine of x, sine of 2x, sine of 3x, sine of 4x, so forth. So think of these as dilates of the nth order Bessel function. These functions are orthogonal with respect to the inner product. F dot g is the integral from 0 to a of f of x, g of x times the weighting function x dx. And again, this nu here is fixed throughout this whole problem. It can be checked that if you take any two dilates of this Bessel function, you take their inner product, so j nu n dot j nu m. So that's just the integral from 0 to a of j nu of omega nx times j nu of omega mx times the weighting function x dx. Then you get 0 if n and m are distinct. Now there's not going to be a nice closed form solution, I'm sure, for what this thing is when n and m are equal. So just know that it has to be non-zero. By orthogonality, every continuous function f of x on the interval 0 to a can be expressed in a so-called Fourier-Bessel series. So f of x, now I'm going to use this for converges to the infinite sum from 0 to infinity of Cn times j nu of omega nx. And we have an explicit formula for Cn. Cn is the inner product of f with j nu n divided by the norm squared of j nu n. So in other words, the inner product of j nu n with itself. And one quick comment, I'm putting this sim sign here, approximation sign, instead of an equals, just to mean that this converges. Because convergence is a little bit tricky when you're talking about convergence in norm and you have a weird weighting function like w of x. So personally, I consider this to be equals, but I know that there's people who might raise a finger for highly technical reasons that are way beyond the scope of this class, or really beyond the scope of the math that I usually do, who might not like that equal sign. So I'm going to leave it like this, and hopefully this middle ground will please everybody. Here's a picture of the Bessel functions of the first kind. I think I've showed this to you before. So here's the formula for the Bessel functions, and here's a picture of the first 6 from n equals 0 up to n equals 5. And I want you to pay careful attention to this red curve, j0 of x. This is the only one that does not go through the origin. And I'm saying pay attention to it because on the next slide, I'm going to show you this function and some of its dilates. Here is an example of a Fourier-Bessel series from the first Bessel function, j0 of x. So let me start with this ODE at the bottom. So the derivative of x times y prime equals negative lambda x squared. This is the parametric Bessel's equation when nu equals 0. And if you solve this, then any solution f of x, I think you probably need mild boundary conditions. So suppose that solution has a root at 1 and is its derivative is 0 at the origin. I think you probably need that. So you can write any solution with those boundary conditions as a linear combination of these dilates of this Bessel function. So here's the ordinary Bessel function. That's the one that was in red in the previous slide. It goes down here in cycles. And then here are some of the first few dilates. This purple one is when n equals 1. So j naught of omega 1x. This gold one is j naught omega 2x. And this green one is j naught of omega 3x, and so forth. And just to remind you what this j naught function is, this blue one, it's given by this equation right here. This is the equation for the Bessel functions with nu equals 0. So I think this is just absolutely remarkable that you can get an ODE like this. And simply because this differential linear operator is self-adjoint, you can derive all this theory, and using linear algebra and orthogonality, you can take any solution to that and write it as a linear combination of these functions. That just seems too good to be true. Here's another example that I found on the internet that I really like, although like all of these, they are really messy, and I'm not showing you all of the gory details, just the big picture. So this is a Fourier Bessel series from the third Bessel function, j3 of x, or I guess the fourth if you start from 0. So here's a function that was, arbitrary function that was picked, f of x to be x cubed on 0 to 10 and 0 elsewhere. So 10 cubed is 10,000. That's way above here, so I can't really draw this that well. But so j cubed is going to be, sorry if this is not really to scale, it's going to look something like that, and then it's going to drop down, and it's going to be 0 to the right of that. So this piecewise continuous function, we can actually write as an infinite series of these dilates of Bessel functions of, I almost said of the third kind, no, of order 3. And of course, at this discontinuity, it's going to converge to that midpoint. So here's what the function j3 looks like. So we're talking about dilates of that. And what is graphed here, these are not the dilates of the function. These are the first 5 partial sums. So recall that a partial sum, S capital N, is the sum from, here it's going to be the sum from n equals 0 to capital N of Cn j3 of omega n x over 10. So I'm just going to guess that these sums are arranged in increasing order. So in other words, this is, let's see, so n0, we probably don't want the 0th one. So this is probably S1, S2, S3, S4, and S5. And if you add up infinitely many of these things, it's going to take a whole lot of them. And convergence is, again, it's not point-wise like you normally think. It's with respect to this weird weighted norm that I won't get into, but eventually this thing will, in norm, converge to this crazy discontinuous function right here. Let's move on to the third example. This is called Chebyshev's differential equation. Now consider the following Sturm-Liouville problem on the interval -1 to 1. So negative d dx of the quantity square root of 1 minus x squared times dy dx equals lambda divided by 1, the square root of 1 minus x squared times y. And here p of x is this guy, square root of 1 minus x squared. Q of x is 0. And the weighting function w of x, this is weird. This is 1 over the square root of 1 minus x squared. Now, personally, I would make this the open interval for multiple reasons, because I don't want to include the endpoints, because p of x is 0 then, and even worse, the weighting function is not defined, and that's all sorts of problems. But I guess you can make some argument about convergence at the endpoints. People do it. People do it on this closed interval. It makes me a little nervous, but apparently it does work out. I'm not going to argue with it. If you go ahead and solve this, you can find that the eigenvalues are very simple. They're just n squared for positive integers n. And the eigenfunctions, so if you plug this back in for lambda and you simplify this ODE, what you get is Chebyshev's equation. This looks much simpler. 1 minus x squared times y double prime minus xy squared plus n squared y equals 0. So when you see things like Chebyshev's equation and Legendre's equation, and there's things like n squareds in them, Some people write them as L's or P's or K's. Those typically are the eigenvalues. Here I'm just showing you why this thing can be cast as a Sturm-Liouville problem. Now, just like Legendre's equation and the example that we solved when we studied power series, one of these solutions is a polynomial. So for each n, we get a solution that's a degree n Chebyshev polynomial, and that's defined recursively as follows. So the first one, t naught of x is equal to 1. t1 of x is x. And then the n plus 1th polynomial is just 2x times tn of x minus tn minus 1 x. These polynomials are orthogonal with respect to the inner product defined as f dot g is the integral from -1 to 1 of f of x g of x divided by the square root of 1 minus x squared. Remember, that is the weighting function. Now, I guess it doesn't really matter if it's defined at the origin or not. We know how to deal with improper integrals, and so I guess that's why they say this is defined on the closed interval, and they can get away with it. It can be checked that if you take the inner product of any two Chebyshev polynomials, so recall what the definition is of this integral, then that is pi if m and n are equal to 0. Otherwise, it's 1/2 pi times delta mn. In other words, if m and n are different, then it's always going to be 0. And if m and n are the same, it's just 1/2 pi. So a lot like Fourier series, there's this annoying case when n equals 0, and otherwise you're off by a factor of 2. By orthogonality, and by the Sturm-Liouville main theorem, every function f of x that's continuous from -1 to 1 can be expressed using Chebyshev polynomials. So that means that this function can be written as this infinite sum from n equals 0 to infinity of cn tn of x. And I'm saying it converges instead of it equals. Essentially, you can think of it as equaling. And like with Fourier series, like with Legendre polynomials and Bessel functions, we have an explicit formula for the cn's. It's just the inner product of f with tn divided by the norm squared of tn. And since we have such a simple formula for this, well, if n and m are greater than 0, then this formula cn, since we know that tn dot tn is 1/2 pi, is just 2 over pi, that's 1 divided by this, times f dot tn. So that is both simple and amazingly powerful and remarkable at the same time. Here's a picture of the Chebyshev polynomials. I should say these are of the first kind. If you Google them, you will get Chebyshev polynomials of the second kind as well, sort of like Bessel's equation. There's of the first kind and of the second kind, and they satisfy different ODEs, and they're related to each other. I encourage you to Google this and look into it. So the first ones are 1x, 2x squared minus 1, 4x cubed minus 3x, and so on. Here's the first 8 of them. And here's what the first 6 of them look like. And again, I think it's amazing that these things are basically, they're orthogonal. So they're basically perpendicular with respect to that continuous version of an inner product with that weird weight, where the weighting function is 1 divided by the square root of 1 minus x squared. That's remarkable that they look like this and that we can actually express functions as infinite sums of these guys. Finally, our last equation is Hermite's differential equation. So now I want you to consider the following Sturm-Liouville problem on the whole real line. Now, I didn't define this formally before, but I think I did say that there is a distinction between a regular Sturm-Liouville problem and a singular one. And this is an example of one that's not regular because the interval is infinite. There are a few other conditions which will make a Sturm-Liouville problem fail to be regular. This is the most blatant one. So the ODE is negative d dx of the quantity e to the negative x squared times dy dx equals lambda e to the negative x squared y. So here, p of x is e to the negative x squared, q of x once again is 0, and the weighting function w of x is e to the minus x squared. The eigenvalues of this Sturm-Liouville equation are 2n for any positive integer n, and the eigenfunctions solve Hermite's equation, which is actually really simple. If you multiply this thing out, you get y double prime minus 2xy prime plus 2ny equals 0. I know you're thinking, wait, what happened to the e to the minus x squared? Well, it cancels out. If you solve this equation, you can do this using the power series method. As before, one solution is a degree n polynomial called a Hermite polynomial. And it's fun to just Google this and look at all the definitions. There's a whole bunch of ways this thing can be defined. Here are two ways. So hn of x can be defined as negative 1 to the n, e to the x squared, times the nth derivative of e to the negative x squared. And that is remarkably equal to the following expression. 2x minus d dx, that's not a typo, there's nothing that should be there. This is a differential operator. Raise that to the nth power, and then apply it to the function 1. And remarkably, that's equal to this expression. And even more remarkably, this expression doesn't even look like a polynomial. It's got e to the negative x squared and e to the positive x squared, and somehow when you take these derivatives, everything cancels out. So fun exercise. Fun is a little bit in quotes there. Verify that these things are actually the same. Caveat, this is not something that I've ever done, nor will I ever probably do. It's actually probably not that bad, but it's probably worthwhile to do. I encourage you to do it. Easy for me to say, right? However you want to express these polynomials, they are orthogonal with respect to the inner product inherited from the Sturm-Liouville problem up here. So that's f dot g equals the integral from negative infinity to infinity of f of x, g of x, e to the minus x squared dx. If you think about it, that's really remarkable. So why are they orthogonal? Well, they're orthogonal because they are eigenfunctions to a Sturm-Liouville equation. And we've built up our theory of linear algebra. It wasn't all that advanced. And we've done that, and did that integration by parts trick, and we've gotten that the eigenfunctions are always orthogonal, which means that this crazy integral over the whole real line of these two different polynomials, for different n's that is going to be 0. So this technical fact about integration follows basically from theoretical linear algebra. That is amazing. It just underscores how powerful and how valuable it is to build up the mathematical theory behind very applied problems in physics and engineering. And it really shows you how all of these areas are tied together. If you compute the inner product of two of these polynomials, so say hm and hn, by definition, that's the integral over the whole real line of their product times e to the negative x squared dx. You actually get a very simple formula. You get the square root of pi times 2 to the n times n factorial times the Kronecker delta. So again, this is 0 if m and n are different, and 1 if they're the same. By orthogonality and the main theorem of Sturm-Liouville theory, every function f of x that has finite norm, in other words, the integral of f squared times e to the negative x squared over the real line is finite, can be expressed using Hermite polynomials. In other words, there is some unique infinite linear combination, Cn Hn of x, that converges to f of x in that weird norm with this weight. And we have a formula for the Cn's as before. So Cn is just the inner product of f with hn over norm hn squared. And since we have a formula for that, this thing up here, that's just the inner product of f with hn divided by square root pi times 2 to the n times n factorial. Here are the first 8 Hermite polynomials. So the first couple are 1, 2x, 4x squared minus 2, 8x cubed minus 12x, 16x to the fourth minus 48x squared plus 12, and so on. And notice that the coefficient of the nth one is 2 to the n. Now they can be rescaled. I think it's just by 1 over 2 to the n. So this first coefficient is monic. And in mathematics, probabilists, people who study probability theory, like to use those. And so those are called the probabilist Hermite polynomials. And these here are called the physicist Hermite polynomials. So two different forms. There's not too much difference between them other than just they're scaled differently. Here's a picture of these Hermite polynomials, the physicist ones, so the ones that I'm showing you up here. I mean, these things look like random functions, like a toddler is scribbling across the page. And yet these things, any function that is square integrable in that norm with the weighting function e to the negative x squared, can be written as a linear combination of these guys. And this is just what they are from negative 2.5 to 3.5. I mean, imagine on the whole real line. Now, some of these go off to, I guess these all go off to infinity, and so you may worry about that convergence, but that exponential function, e to the negative x squared, kills these things off pretty quickly. And again, it's convergence in that weird norm. It's not what you normally think of as pointwise convergence. So this is well at the graduate level, beyond the scope of this class. But if this piques your interest, I encourage you to continue taking analysis courses and take a course in functional analysis and or harmonic analysis in graduate school. Now, here's the last slide. I'm going to go off on a bit of a tangent. I guess this whole lecture was a tangent, but hey, it's a fun one. So I'm going to tie this into quantum physics. So there are these things called Hermite functions that can be defined from the Hermite polynomials, or the physicist versions, as follows. So psi n of x is 1 over the square root, that's this exponent, of 2 to the n factorial square root of pi times e to the negative x squared over 2, that was like a Gaussian, times the nth Hermite polynomial. So that's the nth Hermite function. That can also be written, not at all clear that these things are the same, common theme, as negative 1 to the n times 1 over the square root of 2 to the n factorial root pi times e to the negative x squared over 2. So again, this so far looks good. I mean, you have these terms that are the same as this one, but now you have the nth derivative of e to the negative x squared. That all comes down to the fact that there is this way to write the Hermite polynomials using the nth derivative of these exponential functions. So this is the nth Hermite function. These things, they contain this exponential function in them, are orthonormal with respect to a much more standard inner product. F dot g is just the integral from negative infinity to infinity of f of x, g of x, dx. So you can sort of think of these things as like absorbing that weird weight in there. Now, every real valued function, f, that is square integrable, can be expressed uniquely as an infinite linear combination of these Hermite functions. So again, we're getting rid of this weighting condition, we're absorbing it into the function, and now we're just writing a normal function using these Hermite functions. And because the psi-n's are orthonormal, we have a very simple formula for the coefficients Cn. Cn is just the inner product of f with psi n. We don't need to divide through by anything because this thing has unit length. So again, think of this as the projection of f onto the psi n component. And by definition, this is the integral over the whole real line of f of x psi n of x dx. These Hermite functions are solutions to the time-independent Schrödinger ODE, which is negative y double prime plus x squared y equals 2n plus 1 times y, which you may prefer to write as negative y double prime plus x squared minus 1y equals 2ny, only because this 2n, these are the eigenvalues of Hermite's differential equation. So the time-independent Schrödinger ODE, this arises from the time-independent Schrödinger PDE. And this is a general theme that when we solve PDEs, we separate variables and we put all the variables in time on one side and the variables of position on the other side, and we get ODEs. And in the spatial domain, the ODEs that we get are boundary value problems, and they end up being Stroum-Liouville problems. So that's where this stuff is going to arise, and that's what we are doing next, because we are now at the end of the section of Stroum-Liouville theory, and the next lecture will be on partial differential equations. So this is a fun place to stop, not just this lecture, but this section of lectures. And in the next section, you will see how this stuff applies to things like heat flow and waves on surfaces and on one-dimensional objects. So it's a lot of fun. Stay with us.